السلام عليكم. نتمنى تكونوا بخير وعلى خير وعلى أحسن حال، ومرحبا بكم في هذا الدرس في مادة الفيزياء للمستوى ثانية بكالوريا، شعبة العلوم التجريبية، العلوم الفيزيائية، المسالك الدولية، خيار انجليزية. هذا الدرس هذا غادي يتم باللغة الإنجليزية. الدرس غادي يكون كيتحدث على تطبيق من تطبيقات قوانين نيوتن، ألا وهي كواكب والأقمار الاصطناعية planets and artificial satellites. Planets. The course. Okay, the first section is heliocentric, geocentric frames. So in this course we are going to study the motion of planets around the sun and also the motion of satellites around the Earth. For that we need two types of frames. So the first frame is called a heliocentric frame. Helios means the sun in Greek. Centric means that the center of the sun is the origin of the frame. So the definition of this frame is the following. The origin of the heliocentric frame is the center of the sun. So as depicted here in this image. So the origin of the heliocentric frame is the center of the sun, and its three axes are pointing towards three distant stars. So the three axes of the frame are pointing towards very distant stars. Let's say, for example, that this axis is towards star alpha, this one towards star gamma, and this one towards star beta. So this frame is mainly used to study the motion of planets around the sun, and it is assumed Galilean. So we use this frame to study the motion of all the planets that goes around the sun in the solar system. Like, for example, I give you some images, okay, of the solar system. So for example here, so here's the sun, and here's all the planets of the solar system. Okay, so to study the motion of all these planets around the sun, we need the heliocentric. This is another image. Okay, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. Next, the geocentric frame. So geo refers to the Earth. Centric, the same thing. Means that the frame has the origin of the frame is located at the center of the Earth. Okay, so the origin of the geocentric frame is the center of the Earth, and its three axes are pointing towards three distant stars. So this is the geocentric frame. This is an image of the Earth, and as you can see here, the center of the frame is located at the center or at the origin of the Earth. And as you can see here, the three axes, okay, of the frame are the same as those for the heliocentric frame. They are pointing toward the same three distant stars. So this frame is used to study the motion of natural or artificial satellites around the Earth. So we use this frame to study the motion of anything that orbits the Earth, mainly the moon, which is a natural satellite, and artificial satellites. Here's an image of the satellites that orbit the Earth, as you can see here. It's not realistic, but it just gives an idea about this orbiting. Here's another image. This is the actual number of satellites orbiting the Earth, and the size of the satellites has been exaggerated. Okay, the actual size really is very small, much smaller than this. So in conclusion, in order to study the motion of planets around the sun, we need the heliocentric frame, and to study the motion of objects like satellites, the moon, etc. around the Earth, we need the geocentric frame. Let's move now to Kepler's laws. And he was famous for his planetary motion laws. So the first law states that all planets move about the sun in elliptical orbits, having the sun located at one of the focus points. So as you can see here, the trajectory, the orbits, okay, of all the planets around the sun are not circular, as you may have seen in some pictures, but they are elliptical, like this one. Okay, this is an ellipse. This is an ellipse also, and mathematically in geometrics, an ellipse has two focal points, f1 and f2. So all the planets around the sun have orbits like this, circular, elliptical, with the sun being at one of these focus points. Okay, so this is the first law. The second law states that a radius vector joining any planet to the sun sweeps out equal surface areas in equal length of time. So what does this mean? This means that, let's say for example that this is the sun and this is the orbit of the earth. So let's say that the earth starts from here and sweeps out an area A1 to arrive here, and this motion takes 1 month. And let's say that the earth arrives at this point and makes this motion, sweeps out an area A2 in the same period of time, in 1 month also. So if we measure the area, the surface area A1 and the surface area A2, we find out that they are equal. It means that the planet sweeps out equal surface areas in equal amount of times. This suggests that the velocity here of the planets when they are near the sun are greater than the velocity when they are far from the sun. Okay, it goes like this, slowly here, and when they arrive around the sun they accelerate. So this is the second law of Kepler. The third law of Kepler states that the square of the orbital period t of the planets are directly proportional to the semi-major axis A of their orbital. Now, the orbital period t is the time taken by a planet to go around the sun once, okay, to complete one revolution, okay, around the sun. This is the period, okay, the time taken by a planet to do a whole round or a whole revolution. Okay, so this is the orbital period. So the square of the orbital period of planets are directly proportional to the semi-major axis A. So the semi-major axis is this length, okay, this length. So this is the ellipse, that is the shape of the orbit, and the semi-major axis is the distance between the center of the ellipse and the vertex, okay, of the ellipse, this distance. So t squared over a cube is equal to k, some constant, okay. This is why it says proportional, and Kepler find out that k is equal to this value. So k is constant and it is the same for all planets. So all planets abide by this law, okay. So this law can be applied to all the planets around the sun. So you take their orbital period square, you divide it by a to the power 3, you find out the same constant, which is this one, okay. So this is the third law. Okay, now let's move to the third section. Okay, before that, just a small remark. So from now on we will assume, for just simplification, we will assume that the planets and satellites will have circular motion, which means that the orbits are now circular just for simplification. So section 3, we will begin by the motion of planets around a star. So let's study the case of the Sun and the Earth, for example. So here's the Sun, okay, S, and here's the Earth, T, okay. So this is the trajectory of the Earth, okay, a part of the trajectory, okay. So the first thing to note is the forces. So we are going to study the motion of the Earth around the Sun. In this case, the Earth is subject to a force, which is the gravitational force, the gravitational attraction from the Sun. So this is F of the Sun, the force that the Sun acts on T, the Earth. So F S on T is the gravitational force that the Sun, S, acts on the Earth, T. Next, this force is always centripetal. So F S on T is centripetal, meaning that the vector goes towards the center of the circular trajectory. So this vector is always facing the center of the trajectory, which is the center of the Sun. We call it a centripetal vector. So the acceleration A is also centripetal. So we are going to see that the only force that applies on the Earth is the gravitational force, and applying Newton's laws, F is equal to ma. It means that the direction and orientation of F is the same as A. So A will be something like this. And the last bullet point is for the velocity, and we know that the velocity v is tangent to the trajectory. So v is actually like this. Okay, so section 1, subsection 1, proving that the motion is uniform and circular. So we are going to prove that the motion is uniform, meaning that the velocity is constant, and circular, meaning that the trajectory is a circle. So for this, we are going to apply Newton's second law on the Earth. Okay, and for that we are going to follow the 5 steps. Okay, so the first step is to define the studied system. In this case, the studied system is the Earth. The second step is forces. So in this case, we have only one force, which is the gravitational force, F, that the Sun S acts on T, which is equal to G times mt, which is the mass of the Earth, times ms, which is the mass of the Sun, over r, which is the distance between the centers of both the Earth and the Sun, and so this is r. Okay, so g times mt times ms over r squared times n, which is the normal vector, okay, that goes in this direction. So this is the vector n. So this vector is a unit vector, meaning that the magnitude of the vector is 1, is unity, is just for to give us the direction and orientation of the vector force F. So these are the forces. Now the third step is choosing a frame. So since we are studying the motion of a planet around the sun, we are going to use the heliocentric frame. So we study the motion, the system in the heliocentric frame assumed Galilean and the base we are going to use Frene base in Frene base. So this base is used when the motion is circular. Okay, in this case it will be T U N. So this is the point T, this is N, and U is going to be a vector like this. So U is the unit vector tangent to the motion, N is the unit vector that is normal to the trajectory and centripetal, which means that it faces the center of curvature. Now the fourth step is applying the Newton's second law, or on the system, the sum of external forces is equal to m times the acceleration of its center of inertia. There is only one force, so F S on T is equal to m Ag, which is equal to G times mt times ms over r square and equal to m Ag. So m is the mass, is the mass of the earth, mt, like this. So we are going to call this equation 1. The last step is projection. So projecting equation 1 onto the TU axis gives, so since this vector is along n, is perpendicular to u, so its projection over u is 0, which is equal to mt times dv over dt. So as a reminder, we have a, which is equal to at plus an. At is equal to dv over dt, and an is equal to v square over o, which is the radius of curvature. So this is just as a reminder. Okay, so we found out that 0 is equal to mt dv over dt, which means that dv over dt is equal to 0, which means that the velocity is constant. So the derivative of some function when it is equal to 0, it means that the function is a constant. So this means that the motion is uniform. So far we have proven that the motion is uniform. Now projecting projection 1 onto the other axis, Tn, gives, so this vector is along n, so it's gmt ms over r square, which is equal to mt v square over rho. In this case, rho is equal to r. Rho is equal to r, which is the radius of the trajectory. So simplifying, so this gets simplified by this, square gets simplified by this, and we end up with R equal to G ms over v squared. So I've already established that v is uniform, which is constant, and we know that the mass of the sun is constant, and g is the gravitational constant, which is constant. So this means that r is constant, and this means that the motion is circular. Wherever you have a motion in which the radius is constant, it means that the motion is circular. The trajectory is a circle.